Daniel. Thanks for coming to my talk. So as the title suggests, this talk is inspired by Orwell's 1984. And for those of you who have read the book, this is quite a bleak and negative book, and you might think, how can it actually teach us anything about programming? And my goal in this talk is actually to take some ideas from the book and translate them into concrete programming practices that we can use in our daily jobs and actually do something constructive with it. But first, a quick recap of the book. So how many people here actually read the book? Oh, quite a few. Okay. So just a very quick recap of main concepts from the book, just to have a background. So the book describes a dystopian future governed by under the regime of the party, which controls and sees everything. And at the head of the party is one of the most iconic figures from the book is Big Brother, who is always watching. And one of the methods of control is through the language that the party uses, which is called newspeak. So newspeak was designed to limit the freedom of expression, and some examples of newspeak are the following things. So thought crime is what happens when you're thinking something that the party forbids. And non-person is what happens to you when you actually do such a crime. So you become erased from history and from all existence. And double plus and good is just an example of how we can make the language more compact by reusing small bits of small atoms from which we construct phrases. And here's the focus of the book. These are the party slogans that are repeated through the book many times. So war is peace, freedom is slavery, and ignorance is strength. And you might think that those are not the best slogans to live by. You might be right. But for programming, actually, they're quite good inspiration for various ideas. And you can read this list as a sort of an outline of this talk. So we're going to take each slogan and map it into a concrete technique that we can use and apply in various contexts. So a quick disclaimer before we actually begin. So this is just an analogy. Don't take it too seriously. Whatever you're doing, don't think that you're thought criminals. Even if you're doing Java all day long or something, it's totally okay. I'm not here to judge. Nonetheless, remember that always Big Brother is watching, so, be careful. So to our first slogan, war is peace. The examples are going to start pretty basic, but I'm gradually going to ramp up the sophistication, and hopefully we'll have examples for everybody. And before we can discuss war, let's see what do I mean by peace. So I claim that this is peace, and this is quite scary, and you don't actually have to read it. It's here just to intimidate you, and so I'm just going to hide it away. And the reason why I call this peace is because this code embraces a number of enemies and lives with them in peace. And those enemies are specifically side effects immutability, which makes reasoning about the code more difficult, and nullability, which forces us to scatter various checks to see whether things are present or not, and again obfuscates the flow of the code. Exceptions, which make following the code even more difficult than it already is. And multiplicity is the little ritual we have to make to do something in a loop. So if we want to have the same action many times, we have to do a whole thing just to make it work many times. And all these things are examples of what we call effects. And typically effects make our code more difficult to read, write, and comprehend. And this is peace, the previous slide. The code on the previous slide embraces all of these enemies and lives with them in peace. And the idea of this segment of the talk is to open a war against effects and see how we actually gain real peace in our code. So, and before we can start the actual war, we'll lay out the battlefield. So for this purpose, I'll use a toy example. One of the recurring themes in the book is that 2 plus 2 equals 5, and that the party can make you believe it. And as programmers, we can actually make it a reality. So we can actually model this problem as a concrete thing and see how it goes. So we have here a small language for arithmetic expressions. So we support addition, multiplication, and plain numeric values. And we can write a small evaluation function for this language. So the function takes an expression, produces a number, and so the usual cases we just evaluate the sub-expressions and then do the right action, and obviously 2 plus 2 equals 5. And then we can use this function, and it works as you might expect it to. So this is the example I'll be using for the battlefield. And we can move on to our first enemy. So side effects and mutability. Hopefully for this crowd, I don't actually have to convince you that side effects and mutability are pretty dangerous and really hard to work with. So ideally, the language that we're using should make it difficult or even impossible to express them. And most languages, Scala included, are not that good in limiting this freedom. And so I'm just going to pretend that side effects and mutability just don't exist in our language and just not use them at all during this presentation. And so this deals with our first, and maybe we can move on to the second one. So what is nullability? Nullability is when something can be potentially missing, like the ampersands in the book. And since we're dealing with numbers, we're going to make a number disappear. So here's a variation of the evil function from before. But in this case, the number 7 can disappear. It becomes null. So, and the fact that it can disappear makes us pay quite a heavy price. So we have to scatter null checks everywhere. And so the flow of the code is not as apparent as it was on the previous slide. And also it's dangerous, since the compiler knows nothing about nulls. And if we forget to check something somewhere, we'll just have a runtime exception, which is probably not so nice in production code or whatever. But nonetheless, this example works. So we can evaluate the new expressions. And if we have a missing number, we get a null. So the question is, how can we clean up and make this code more readable and easier to make correct? And for this purpose, we'll have to analyze our enemy and actually understand its essence. So what is nullability? And one of the best ways to understand the essence of something is to come up with a type that describes this specific concept. So in our case, we'll have a new type called nullable of A, which stands for a computation of type A that may be missing as a result. And we have two cases. One is when the value is present, so we just wrap the A value with the value constructor. And the other case is when the value is missing, and so we just have a constant which is missing and stands for the null in the previous slide. And so with this in hand, we can rewrite our nullable evil function, but this time we're using nullable of int. And so everywhere where we actually have a nullable of int, we have to pattern match and verify that everything is handled. So in this case, the code is still kind of hard to read since we have this like nested flow, which is kind of hard to follow. But nonetheless, at least the compiler now knows that we're dealing with nullable values, and so it enforces these pattern matches for us, and so we can't get it wrong at least. And it works as you might expect it to. So evaluating two present values is okay, but evaluating something with a 7 is missing. And so it is an improvement over the previous slide, but it's still kind of obfuscated. And so we have this like repetitive pattern matching all over the place. And the question is, how can we get rid of it? And one of the tools as Scala programmers or as functional programmers to deal with such things is to define higher order functions. So a function that will take care of some repetitive pattern for us. In this case, we'll define the chain nullable function, which will handle the pattern matching for us. So it takes a single function argument, which takes a value A and produces a nullable of B and produces as a result a nullable of B. And what it does for us is pattern matches on the current computation. If it's present, it applies the function. If it's missing, it just propagates the missing case. And so this takes care of pattern matching for us, and we won't have to do it ourselves anymore. And so we can rewrite the example again. As you can see, no more pattern matching. So the code is much less repetitive and more readable in my opinion. But still, it's kind of nested, and it won't scale. If you have many nullable values, it's going to nest all over the place. So we're going to have like a diagonal of chain nullables. And the question is, can we do even better than that? And so with a bit of practice, and the more you're familiar with functional programming, you'll recognize the pattern immediately. And specifically, this pattern is called the monad abstraction, and crowd favorite everywhere. So for our purposes, the monad abstractions, the main function of the monad abstraction is the flatmap function, which is you can view as a generalization of the chain nullable function from before. So instead of nullable, we're using any sort of context that wraps a value. And it can read as a generalization of the previous chain nullable. So given an f of A and a function from A to f of B, we produce an f of B, like chain nullable did with nullable values. And having recognized that we have a monad in place, we can recall that Scala has special syntax for monads, specifically the monad comprehensions, or for syntax. And we can use this to rewrite our example again. In this case, as you can see, the flow is much cleaner. We have no more nesting. And what's essential here is that we're dealing only with the happy path. So the happy path is where the values are present, and this is what we're actually writing. And the flat maps, or the for syntax, which desugars into flat maps, takes care of propagating missing values as appropriate for us. And so having completely isolated our enemy behind a type and a dedicated abstraction, we've managed to get our code into real peace. So we don't have any more obfuscation from nullability. And so we can move on to our next enemy. So exceptions. So armed with the experience from before, we'll start directly from the type. So if we want to understand our enemy, we have to come up with an appropriate type for it. And so in this case, we'll have a new type called accept of error and A. So accept of A stands for a computation that may fail with an error of type error or produce a value of type A. And again, we have two cases. One is when the value is present, so the OK value. And the other is when we have an error, but this time it's not a constant. It actually has an error value which we can actually use for further computation. And since the flat map function or the monad abstraction from before was so useful, we'll define it straight away. So it's quite similar to chain nullable from before. We just pattern match on the current value and apply the function, the callback function as appropriate when it's present. But if we have an error case, we just propagate it onwards and continue the flow with an error. And so here's an example of an evil function that uses the accept type. So as you can see now, multiplication became forbidden. But as you can see, the core functionality of this code is exactly the same as before. We didn't change anything. The force syntax just took care of doing all the heavy lifting for us. In this case, again, it propagates all the error values as appropriate, but we are living on the happy path. So our code is still not obfuscated by the use of exceptional values. And so we can, again, live in peace and don't have and remove all enemies from our code. And so you can use it as before. It works as you might expect it to work. And so again, where the enemy is vanquished, we're in peace. And so again, war came out good. And we're now ready for our last enemy, multiplicity. And so what does it mean to have multiplicity? It means that we have a single computation that can produce multiple values. It's like the quote from the book, the hero of the book sometimes encounters the state where 2 plus 2 can be either 3 or 5, and it's kind of hard to tell apart. And so what does it mean to have a computation that produces multiple values? It means that we have a list of A's. And so since the standard library already defines flat map for a list of A's, we don't have to define it ourselves, and we can just use the list of A for the next example. So here's an evil function that produces a list of numbers. Notice that addition of 2 and 2 yields 3 and 5 together, but still the core logic here is exactly the same as before. Didn't change anything. We're still on the happy path, and nothing special is needed just to accommodate the new type here. And when we use it, we can see that the flat maps or the force syntax here takes care of cross-computing all possible variations of the computation and produces a list of results in return. And so again, by being at war with the effect, our code again remains in peace. And this concludes our little war on effects here. And so to recap, we should recognize enemies in our code for what they are, effects like nullability and exceptions. We should look at their essence and try to represent them in an explicit way, precise and explicit way, preferably a type, which is always very precise. Along with the type, we should try to hide away the interface of working with the enemy behind some concrete abstraction. In our case, it was the monad, but there are many other abstractions as well. And so once you've done all that, you've opened an all-out war against effects. Your code can be truly in peace, and so war is peace. So, to our next slogan. Freedom is slavery. Okay, so again, I'll start by illustrating what do I mean by freedom. So one day, your boss comes in and tells you that the library, the arithmetic expression library that we just produced is production ready. Let's just ship it to our clients and let them work with it. And so we do that, and our clients are using the library, so producing expressions, like more and more involved expressions, going completely insane with them. And then one day you see this expression. And you probably don't see what's wrong with it, but it's obviously wrong. And it's wrong for the following reason. So if you focus on the numbers, you can see like there's a serious problem here, or maybe you don't. But now you definitely can see it. So this is obviously a subversive message against Big Brother in disguise. And your boss sees it, and he's not happy about it, not happy about it at all. And obviously this cannot pass without a punishment. And so That's it. And while we're at it, we can now think about the error of our ways and how did we get into this place. And we can actually, the problem is quite simple. We can look back at our definitions and see the problem quite clearly. So if you look at our original expression language, you can see that the constructors for the various cases are completely exposed. So we give our clients the freedom to use our data types the way they want to. And for the freedom that we gave them, we are now the slaves of their choices. So if they produce incorrect values, we're now enslaved to this and have to accommodate the incorrect values ourselves. And so it's possible to create the wrong expression from before. And so to fix this, the problem is excessive freedom. To fix this, we need to somehow reduce the freedom in our code. And in this case, the fix is also simple, just as the problem. So to be able to reduce the freedom of the code, we're just going to forbid creating new expressions in client code. So by marking, this is call specific, but the idea applies generally. By marking the case classes as sealed and abstract, we're forbidding client code from creating expressions at all. So we have no freedom at all at the moment. So they can't create expressions. Obviously, if they can't create expressions, they can't use our library. So we have to accommodate some measure of freedom, but just a little bit. And for this purpose, we'll use what we call smart constructors, so an apply function that creates expressions for us. But they're smart in the sense that they actually validate their input and produce a nullable value. So since war is still peace, we still use the same abstractions from before. And so if the expression is valid, we produce an expression. But if it's not valid, we get a missing case. And so the implementation is quite simple. Just pattern match on our inputs. If it's the wrong input, we produce missing. Otherwise, we create a new expression. We should do the same thing for the other expressions, but since we don't have any special validation, we just do the trivial thing with them. And now using the monolith comprehension syntax from before, using smart constructors is actually quite simple. So we just use for syntax and create new values. And as you can see, when we're creating a valid value, we actually get a value. But when we're trying to create the illegal value from before, the whole result is missing. And so having reduced the freedom of the interface, we're no longer slaves to the choices of our users. So we cannot produce incorrect code by leveraging the library. Now, in general, though, this example was quite simple. Choosing the right amount of freedom for the client code or for any code can be quite tricky. It's not always apparent how much freedom do we want to have in our interface. And so let's try to build a more complicated example where the issues are more subtle than this case. And so again, our boss comes in and says that what we're doing here is censorship. And it's great. We should do like way more censorship than this. And the problem is this censorship was quite primitive, so let's make it more interesting. And so here are a list of requirements for our censorship. So we're going to process expressions. We can either fail with the message or succeed, or as censorship sometimes does, we can silently rewrite the input and produce a new result. Now, since we're already used to working with types and to model every problem with a dedicated type, we can do the same thing here. So type censor suits our requirements. So it takes an expression, which is the first step, and then produces either an error with a string message or an expression when it succeeds. And since this expression is free to be anything, we can silently rewrite it to whatever we want. And so this fits the requirements, and we can try to write a censorship rule with this type. So here's an example. So this rule does a few things together. So given an expression, it silently rewrites 4s into 5s. 7 is still a non-person. We have forbidden various variations of multiplication and addition. But the core logic here is still the same. We're still using the for syntax from before and still on the happy path, and war is still peace, so everything is lovely. And we can use this rule now and to apply it to some expression. And so in this case, here's one example where everything is OK but rewritten. So addition of 4 plus 6 is OK, but 4 has become 5. But the second rule, we did something illegal and we get an error message. And so here we have a small problem. Can anyone see the problem here? No? So we use 7, which is illegal, but we also multiplied by 3 and added 9. Both of them are illegal from the previous slide. But we got only a single message. So we somehow swallowed our error messages inside our result. And it's not a surprise, since our type dictates that we have a single error message, a single string. So it's not surprising that we have a single string as a result. So if the problem is with the type, we can try and fix the problem with another type. So to accommodate the new requirement, so we want to have a list of messages. So instead of a single string, we'll produce a list of strings as their value. And hopefully we'll just accumulate errors as we go along. And so with this in hand, we can, again, write a new rule. So it's quite similar to what we had before, just we're wrapping everything with lists, all the messages. But again, the core logic is still the same for syntax as before, so everything works out fine. And so since we're actually used to the for syntax doing all the magic for us, we hope that everything works out as well. And we try it again, and we still have the same problem. So we do have a list of strings, but the string is still single string, and not a list of all the problems that we have in this code. And so the magic didn't quite work this time, and our boss comes in again, and he says that we're suppressing important ideological content. And that saddens him greatly, since he worked so hard to produce all these messages. But of course, sadness can last only so long, so again, it's replaced with anger. And of course, we get punished again. And the question is, what went wrong again? So what happened this time? The mistake now is more subtle than before. So if we look at our original sensor type, we can see that it uses exceptions to produce a value. And if we can recall that the accept value, the interface to work with it is the monad abstraction. So if we recall the monad abstraction with the flatmap function, this is the way that we use, this is the function that we use to actually operate on the exceptional values. And so if we actually analyze again the flatmap function, we can see the problem quite clearly. So we can read, we can think of f as some sort of action that produces a value. And so we can read the signature as follows. So given an action that produces a value of type A, inspect the value of type A, choose the next action that produces a value of type B, and then return the result as an action of type B. Now the question is, what happens when we don't have an A value? So like in the exceptional case here, when we don't actually have an expression, what are we going to pass into this function? And the answer is nothing, since we don't have anything. And essentially, flatmap forces us to short circuit the computation. So we don't have any choice. We can't proceed to the next action. And so we have to short circuit the whole thing and produce a single error result as we've seen before. And if we look at it from another point of view, the problem here is that we have excessive freedom. Specifically, we have the freedom to inspect the previous value in order to choose the next value afterwards. And this freedom actually was never used. So if we look at our code from before, and this is the same for syntax, just desugared into flatmaps, we can see that rule of B here is independent of rule of A. So we were given some freedom, the freedom to choose actions based on previous inputs, but we abused it. We didn't do anything with this freedom. And for this, we're now paying the consequences of this freedom that was abused. And so in this case, the consequence is the fact that we cannot accumulate any more errors. So we've lost the excessive freedom that we had to choose actions based on previous results is now limits our ability in actually providing some useful output from our computation. And as before, the solution for excessive freedom is to somehow reduce the level of freedom and scale it back to something more appropriate to our current problem. And for this purpose, we'll have to find some other abstraction, not the monad abstraction, that will handle this for us. Luckily, there are many abstractions in the functional world of functional programming, so we can try and choose something more appropriate. So let's start with functor. So functor abstracts over mapping on things. So given an f of a, some a wrapped in a context f, and the function from a to b, we can produce f of b. So this is obviously weaker than monad, since we cannot implement flat map with map alone. But so this is too weak for our purposes, since we can't do much at all with functor, and so we won't be able to actually implement our logic with map alone. So we can try to ramp up the abstraction. So here's another one called Duplicative. It has two functions, but we'll just focus on map2. So map2 takes f of a and f of b, so two values wrapped in context, and a function that works on a and b and produces a c, and combines the two values into a single f of c. Now this is obviously more powerful than functor, since we can implement map with map2 and unit alone. But this is also weaker than the monad abstraction, since we cannot implement flat map using map2 and unit. And so this is sort of a middle ground in the power of abstraction. And what's more critical for our purposes here is the fact that map2 takes the two values completely independently. So f of a and f of b are two actions that are computed one without any input from the other. And so this is a limitation, so since or a constraint, since we cannot choose f of b based on the value of f of a, but this constraint, or lack of freedom, is going to actually help us to achieve our goal, the goal of accumulation of error values. And so we'll see how we can use applicative to actually accumulate errors as desired. So we'll define a new type, just to forget the old history. So the type censorship of A has, again, two cases, a passing case, value A, and an error case where we have a list of strings. Now, previously, we were defining the monad abstraction. Now we'll have, since it didn't work out, we want less freedom in our code, we're going to use applicative instead. And so here's the implementation of applicative for our purposes here. So we have two censorship, one of A, one of B. And now we want to pattern match on them. And so if both cases are passing, we just apply the function to them and continue with the passing case. If either of the cases is failing, we just propagate the errors and move along. And here's the crucial case here is when both actions are failing. And so since they're completely independent, we can evaluate each and one of them, and we can combine the two errors into a single value, produce a new accumulated error with errors on both sides. And this is exactly the behavior that we aimed for when we chose applicative. And so now the censor type becomes a function from expression to censorship of expressions. And we can rewrite our rule from before using the new type. So it's quite similar to what we had before, but now since we don't have the monad abstraction anymore, we can't use for or flat maps. And we have to use map2, so it's slightly uglier, but still it takes care of the happy path for us. But what's crucial here is that rule A and rule B are completely independent. Both are evaluated independently, and then only when both of them finish evaluating, we combine into a new value. So if we have errors on both sides, we'll have errors. We have the composite error on the other side. And we can run this rule on the new input, so it works as previously on rewriting as before. But if we have 3 errors in the expression, we have a list of 3 errors. A list of 3 errors in the result. And so by limiting the freedom of the code, we've managed to achieve our goal, which was error accumulation in this case. So to conclude, freedom on one level, giving freedom on one level binds us to paying on another level. We're enslaved to the consequences of this freedom. So this can be the risk of producing incorrect outputs, as in the first example, or the inability to extract some useful information, like the errors in the second case. But even more generally, limiting the freedom of code helps us reason about the code, since the less the code can do, the more we know about what it actually does at runtime. Of course, one cannot take away all freedom from the code, since then it's unusable, like the functor example from before, where using a too-weak an interface for the purpose, we can't actually write anything useful. And so we have to choose the right level of freedom and give exactly that, but no more, since we're afraid to be being enslaved to the consequences of this freedom. And once you start using well-defined abstractions, mathematical abstractions, like functor, applicative, and monad, and many others that exist in the functional world, freedom becomes something that can be quantified. And choosing the right amount of freedom becomes just a choice of the right step on the ladder of abstraction. And so we can make the process of choosing the right amount of freedom something, if not mechanical, but more systematic. And so we can balance the freedom is slavery slogan as appropriate to our purposes. So this concludes this part. So to our last slogan, ignorance is strength. For this purpose, I'm going to declare some more enemies of the state. So it's a list of things that we probably want to avoid anyways, so it doesn't really matter. But for the following part, I'm just going to assume that they don't exist at all in our language. And it's probably for the best. And so here's a small quiz. So can anyone tell me what this function does? Right?
It's 2 to a number.
No, I lied. Okay, so I tricked you. Of course, the name of the function doesn't actually guarantees anything, obviously, so names can be misleading. But the problem goes deeper. Since the function operates on numbers, the solution space is huge. We can use any function on numbers to produce the result, and so we can't say anything at all about this function. But what happens if we take away from the function the knowledge about the concrete context it operates on? So we erase some knowledge, make ourselves more ignorant of the context. So this is as generic as it gets. Can anyone guess what this function does? So this is the identity function. And so why is it so? So given that this is a parametric function or generic function that takes an abstract value a, we don't know anything about a, so we can't invoke any functions on it. Also, we cannot produce any values of a because we don't know what values to produce. And so if you want to produce a result of a and we have an input of a, we're forced to return the given a as a result. And so this property that lets us reason about generic or parametric functions is called parametricity. And so, which in our case translates to the fact translates to the following: the less we know about our inputs, the more our outputs are constrained. So, from some form of ignorance, we gain some strength in reasoning. Of course, not all examples of not all code that we are writing is actually identity functions. Some code is slightly more complicated. So, but the general idea actually still stands. So, parametric functions are easier to reason about since they are more abstract. We can say they are more constrained, and we can say more about them. But let's see another example. So here's the swap function, where I take a tuple of numbers and try to swap them. Obviously, I have a small bug here that I didn't actually swap anything, which is sad, I guess. But now, what happens if I erase the knowledge about the specific parts of this function? So I don't care that those are numbers. I just care that we have a tuple. And so by setting a and b as type parameters and taking a tuple a of b, the signature of the function actually makes it quite plain about what it's going to do. So given a tuple of a and b and produce b of a, since both of them are abstract, I can't do anything else but swap them. Now, this is actually quite nice for us, but what's more crucial here is the fact that the compiler sees this as well, and so this little bug from before becomes a compilation error. And so ignorance helps us avoid bugs in this case. Again, sort of strength. Now, obviously, again, this function as well is not the most complicated thing that people typically write. And so, my screen works here. Okay. So let's try to build something more sophisticated to illustrate the point that ignorance actually buys us something. And so, as sometimes happens in big organizations, while we were doing our brilliant job of writing expressions, someone else was doing exactly the same thing, and they came up with another language for expressions 2. And in this case, instead of having separate constructors for all the cases, they have like a single binary operation constructor, which takes an operation as an argument. This is quite similar to what we did before, but there's some duplication here, and we would preferably want to avoid duplicating our important business logic from before for this new expression language. And so to avoid duplication in the actual logic, we can write a translation function and just translate between expressions of the new kind to the expressions of the old kind. And this is quite straightforward. So we take an expression of the second kind, produce an expression of the first kind, we just pattern match on a single layer, and we peel it away. So if binary op of plus, it becomes an addition, and then we recursively translate the subparts of the expression. And so this works as you might expect it to. So given an expression of the second kind, we produce an equivalent expression of the old kind. And now we can reuse the evaluation logic from before by just composing the two functions. So if we take an expression of a second kind and want to produce a number, we just convert it to expressions of the first kind and then evaluate. And so we've reused the logic from before, and there's no duplication, which is a nice thing. And it obviously works as you might expect it to. And now, yet again, our boss comes in and tells us that actually our clients are going crazy. They're building like huge expression trees. And what we did here was quite inefficient because to translate and evaluate the tree, we're going up and down the tree twice, once for translation and once for evaluation. And so this is quite wasteful, and Big Brother actually cares about performance quite a bit. And so what can we do? If we look at our eval function from before, you can see we have a problem. So we have two parts to this function. One is the fact that we're actually evaluating something, like returning 5 or doing addition or something. And the other part is the recursive part, is the traversal of the expression tree for the purposes of this function. And so since they are fused together, since we can't break apart the evaluation part from the traversal part, we can't actually fuse this function with anything else. We're forced to do the recursion as we evaluate, and we can't stop it in any way. And to get a handle on the exact problem, let's try to see another example just to illustrate the point better. So here's a similar function that takes an expression and prints it as a string. And we can see a pattern arising here for such recursive functions. So we can summarize the pattern as follows. So for some type A, be it string in this case or int in the second case, we want to recursively convert the parts of the expression into a value of type A, and then combine the resulting A's into a new A and pass it on to the next level. And so what's unique here to each function is how do we combine A's? So in strings we just concatenate them with some operators. With numbers we merge them with the function. But the logic of recursing over the tree and actually traversing it is the same in both cases. So what we'd like to do is somehow abstract away this logic into something more reusable. And we could write a higher order function like we did with chain nullable, but actually the problem goes even deeper than that. So if you look at our original expression, we can see that the expression is what is called a recursive data type. It references itself in its own definition. And we can see that the recursive references happen exactly the same places where we're doing the recursive calls in our functions. And so what we should do is try to somehow factor out the recursive nature of this data type outside the data type and just keep only the logic of being an expression in it. And so somehow erase the knowledge of the recursive nature of this data type. And for this purpose, as we're already used to, we're going to define yet another type. In this case, an expression step of type A. So it stands for a step in the computation of something that relates to expressions that produces a value of type A, be it a string or an int or anything. So we have three cases. Each one corresponds to the constructors from before. As you can see, all the recursive references, the references to the expression from before, are now replaced with A. Okay? And so we made, so add step stands for, suppose we have two parts of an expression that were already evaluated into an A, say a string or an int. It combines them into a single unit for addition. And so you can see that this is the exact same thing as before, but without the recursion. So we kind of separated away the recursive part from the shape of this data type. And so we can try and write the evaluation function from before using this new data type, and we have the following thing. So evaluation of a single step takes an expression step of numbers, it produces number, and produces a single number. And we can read the main branch here as follows. So suppose someone already converted two subparts of an expression into numbers. How do we combine them into a single number? In this case, it's addition. And so this is exactly the logic for evaluation without any of the recursive parts. We're doing just the arithmetic, but no recursion, no traversal, no nothing. So in this case, we managed to separate away two aspects of the function. Again, sorry. Two aspects of the function into separate parts. And we can do something similar with the translation function. So in this case, we're taking an expression of the second kind and producing a single expression step that produces expressions of the second kind. In this case, we're peeling off a single layer of the new expression, producing a new step, and leaving the rest of it, the rest of the handling for subsequent calls of this function. So again, we stripped away the recursive logic from this function. This is just the logic of translation, nothing else. And so having separated the two aspects of this function, of these functions, we can try and fuse them together into a single function that does a single pass over our data to translate and evaluate. And so we can try and write a fuse function that takes a producer of expression steps of x2 and an eval function which reduces expression steps of int into ints, take an input expression 2 and produce a single number. But this is quite specific to our problem. Can't we go more generic, erase some knowledge of the specifics of the problem? And the answer is yes, obviously we can. And so we can translate the type arguments into type parameters. And so in this case, we have something that unfolds A's into expression steps of A's and something that reduces expression steps of B into B. And given an A, produce a B. This is still quite specific to our problem. And again, the same question arises. Can we make it less specific to our domain? Can we work with any generic container of stuff ever? And we can try and do that. So given some container type or some context, f, a, and b, we have a function that unfolds a's into f of a's and reduces f of b's into b's and provide an a, produce a b. And this is as ignorant as we can be. We've removed any possible domain knowledge or anything about the context of this function, and there's nothing else to be done. But the problem is that this is a step too far. We can't actually do anything with this function. Since f here is completely abstract, we have no access to working with it. We have no way of actually doing anything with it, and so we won't be able to implement the fuse function. And so to be able to do something and actually implement the fuse function, we will have to bring back some knowledge about the context. And in this case, we'll need some interface to working with types like f here. And luckily we've already seen an interface of this sort. Specifically the functor interface from before. It takes an f and it lets us map over f of a, produce an f of b. And this is the most simplistic interface we can have for things of this shape, of f's context of this kind. And so with this in hand, we can actually implement our fuse function as desired. So the signature, this is the final signature for this function, reads as follows. Provided we have a type constructor or context f that implements the functor interface, type parameters a and b, and a function that unfolds a's into f of a's and reduces f of b's into b's, given an a, produce a b. And so this is as ignorant as we can be, but still be actually productive and do something. And we've removed all irrelevant details from this function. And one of the advantages of working at this level of abstraction is since the inputs are so generic, the implementation is very constrained. So this ignorance is a sort of a strength that will guide us to our solution. And in this case, we just follow the types. So since the types are so abstract, we can just follow them and fill in the spaces. And so we can start with, we have a value of type A, and we have only a single consumer that takes an A. So we'll just pass it on. So we apply it from A to A, we produce an f of A. Now we don't have any consumers of f of A, so this is a problem. At this point we recall that f implements a functor, and so if we had a function that takes A's to B's, we could turn this f of A into f of B. And it may not appear so, but we actually do have such a function. And if we partially apply the fuse function to its first two arguments, we'll have a function from A to B. So fuse with the first two arguments is exactly a function from A to B. And we can map this over our f. So f map A to B, we produces an f of B. Now we have a single consumer of f of b's. And we can apply this to our value. This produces a B value. And this is exactly the desired result. And so we can return this. And so for me, it's quite amazing that we just followed the types and it produces something. And I can tell you that this is actually the correct result for our specific problem. And before we can actually use it, we have to prove that expression steps is actually a functor. So we have to implement the map function. And so we do it in the obvious way, just apply f where applicable. And with this in hand, we can actually now create expressions of the second kind, fuse two expression step and an eval step, and apply them to the expression and produce the right value. And the fact that we've managed to do this in this completely abstract way and without regard to any specifics of our problem kind of blows my mind to this day. And if you don't actually believe me that it works, since I just written some code and didn't even compile it here, I have a trace of execution. I won't go over it since we don't have any much time, but you can, if you just follow along at home with it, you can see that as we go down the tree, we're translating the levels of the tree, and as we go up the tree, we're reducing the numbers into doing arithmetic on the numbers and reducing them into a single result. And so this trace actually what we wanted. So we have a one up and down traversal of the tree. And again, I still find this amazing. So by removing some information, we managed to make the solution much more obvious. This is quite amazing. So to conclude, we need to strive to remove as much as specific knowledge from our code as possible, since not knowing the context in which the code is running restricts the possible implementations. And since it can't use any specifics of the inputs, the outputs are again constrained. And so we can use this ignorance to our advantage, be it by determining some aspect of the function or by allowing the compiler to help us derive a solution. And so indeed, ignorance is strength, as we wanted to prove. This is one of my favorite quotes from the book. It's right in the point of this part. Okay, so this concludes this talk. So these are the three slogans. So war is peace, freedom is slavery, ignorance is strength. So to sum up, we've seen how each of them maps to something concrete that we can use for our programming. War in effect brings peace to our code. Freedom on one level is slavery on another. And we can leverage ignorance to help us reason about code or even derive it for us. And so if you want to take away something from this talk, just print this out, put it in your office, and just convert people to functional programming with this, like 3 slogans. I think it will be the right way to go. Some further reading for those interested. So the full code for this talk and the presentation itself is present on my GitHub account. The more complete explanation about monads is given in this paper by Philip Wadler. Typiclopedia is a Haskell resource, but still quite useful to learn more about various abstractions that are applicable in the world of functional programming. Have a wide range of various abstractions. More content on the idea that freedom is slavery is given in Runar's talk, Constraints Liberate, Liberties Constrain. Ignorance is strength. So theorems for free is so the parametricity property that I talked about or hand-waved about is formalized in theorems for free, which is an article by Philip Wadler. And the fuse function, which I showed here, is just one example of something called recursion schemes, which is quite a wide topic, and we have talks here about it. But it was first popularized in this article by Meyer and others. And a more sort of down-to-earth explanation of recursion schemes can be found in this blog post series by Patrick Thompson. And that's it. Questions? Questions? Anyone?
Could we go back to the slides where you showed a fuse function? A couple of slides back. Because there is a partial, there it is. Great. So the second method invocation here, right now, below?
Yes.
Below?
What?
Yeah, exactly that. Could you expand on that a bit more? What's going on here? It seems recursive to me.
That hides away the recursive. That's like the only place where we can actually mess up something and just go into an infinite loop. And as I prefixed in the beginning of this part, we're going to ignore infinite loops. But this is the recursion, actually. This forces the code to go map into our expression steps and do something inside them. And it will stop only when we get to a leaf. A leaf in this case is a number or a value expression. Partially applying it, I knew how to partially apply it just by following the types, but knowing that it will actually terminate requires some knowledge of the data type. So in this case, I know that every expression is going to end with a leaf that doesn't have anything to map over, and so this will stop and produce a value and move it back up the recursion, up the stack back to where we came from. Does this answer your question?
It makes it clearer.
Yeah, so it's a quite tricky thing to figure out. I just sat like half a night and just working out the things until it worked out, but it's feasible completely. So
it's just 4 lines, 5 if you count the return value.
Yeah. So yeah. Anything else? No questions? Okay, great. Thank you.